The second paper is specializing word embeddings for parsing by information bottleneck. The speaker is the first author, Lisa Li.
Thanks. Hello. Hello, everyone. I'm Lisa, and this work is done jointly with my advisor, Jason Eisner. Well, that's a long title, and here's one that you can remember. Thrashing word embeddings. Previously, people have used ELMO as a starting point for task-specific representations. Basically, they initialize ELMO and then fine-tune. But the brilliant idea of ELMO is that it's based on language modeling. And the language model has to know everything about the language. So whatever task you do, the relevant information is also needed by the language model. So the information should already be in ELMO embeddings. Now the question is, how do we get the task-specific information out? So we'll focus on how to get syntactic knowledge out. For this paper, we present a general framework of extracting task-relevant information from pre-trained ELMO embeddings. It is a form of specialization, and we will take syntactic parsing as an example. So here's how people fine-tune word embeddings for a task. Imagine a wheat field that sends wheat to the factory that produces cookies. An evaluator's feedback is propagated back to the factory and all the way back to the wheat field, aka genetic engineering. So in an NLP setting, the field is a pre-trained ELMO model which passes word embeddings to the parser, which sends parse cookies to the evaluation scripts. The script should score labeled attachment or log likelihood. In the backward pass, people backpropagate to the parser and all the way back to ELMO model. So it fine-tunes ELMO jointly with the parser. Now we introduce our new idea, thrashing. Wheat has good parts, grain, and useless parts, chaff. Thrashing keeps only the grain. In our case, grain is the syntax, chaff is all the other information that ELMO extracted. That's useful for language modeling, but not for us. So now let's look at our specialization framework. We introduce a new step of thrashing and a garbage can to keep the useless information. In the forward pass, we will start with the wheat, but we keep the grain and throw away the chaff. In the backward pass, we backprop through the thrashing step. And what backprop is doing is to improve the thresher and get better separation of wheat from chaff. Notice that we are not backpropagating all the way to the wheat field. So similarly, for NLP tasks, the thrashing step separates pre-trained ELMO embeddings into specialized taggings and chaff. So, poor ELMO, but at least we don't have to retrain him anymore. The original ELMO already has all the body parts we might ever need, because ELMO was pre-trained for a language model task, which is NLP complete. We just have to decide which parts of ELMO to keep. This embedding thrashing framework can be easily generalizable by swapping black boxes. Now, because we have a different task, ELMO's body will be split differently. So what are the advantages of our model? We only need to train the thresher, not the ELMO parameters. This is much faster. We train on 100 sentences per second. And since the thresher has a smaller parameter space, there is less danger of overfitting if we have a small training set for the task. So now let's train a parser on full ELMO. That's the star on the right. It's pretty accurate, but we overfit because the tree bank isn't big enough. As we gradually squeeze information from ELMO embeddings, it actually improves accuracy a little, just as fine-tuning would. As we keep squeezing, we start losing information too, and this lousy compression hurts parsing accuracy. So how does specialization work? We use an information theoretic method. It's called the information bottleneck. So we introduce, Oscar, who stays actively at the garbage can, demanding and hoping for more trash. Oscar's feedback is backpropagated to make the thresher produce more chaff. So this is our information bottleneck objective we want to minimize. This wants our thresher to discard as much ELMO information as possible, while still keep the syntactic information to help us parse. So the first term is the mutual information between our grain and the dependency parsers, indicating how much information our grain has about the true parse. We want to help the parser as much as possible to choose among parses. The second term is the mutual information between our grain and the ELMO embeddings, indicating how much information our grain retains overall. We want to retain as little as possible. Basically, the first term is to make the parser happy, and the second term is to make ELMO happy. Is to make Oscar happy. So beta is the trade-off parameter. When we have a bigger beta, we have more compression to make Oscar happy. Now let's delve a little bit into the mathematical representation of each term. The first term, by definition, could be rewritten as this: the difference between entropy of parse and conditional entropy of parse given grain. The first term is a constant with respect to the thresher parameter. To evaluate the conditional entropy, we need a probabilistic parsing model. The second term, by definition, could be rewritten as the K-out divergence. And to evaluate this, we need to know P of grain given ELMO and P of grain. I'll show you how these unknown terms appear in our model architecture. So this is our model architecture. We start from an English sentence. We pass it through a ELMO layer to produce the corresponding ELMO embeddings. Then we pass through our token encoder, which parameterizes P of grain given ELMO. We get samples of specialized taggings from the token encoder and pass them to the decoder. The decoder is actually a parser that parameterizes P of parse given grain. So now let's zoom in to see the token encoder. Recall that we are trying to squeeze out useless information. One standard way to reduce dimensionality is PCA. The task-specific version of PCA, CCA, canonical correspondence analysis. Our method is different from CCA because it's stochastic. So what is good about being stochastic? We could choose to keep a different level of compression for each dimension. A CCA could lose information by being non-injective, whereas we can lose information by using the stochasticity and make some dimension noisier. So for some word tokens, we really need all 4 dimensions. As a result, the Gaussian distribution is very spiky and have less noise. But for other tokens, retaining less information will still allow a correct parse. The Gaussian at dimension 3 and dimension 1 becomes flatter and have more variance. We keep little information by introducing more noise to these dimensions. So for example, in English, we can throw away whether an object pronoun was singular or plural. We care about the number of a subject pronoun, but not for an object pronoun. So we'll have more chaff coming out of dimension number 3, making Oscar happy, and dimension 4 is enough to keep Cookie Monster happy. Basically, we use a coarser-grained tag in the object position. So this is the architecture of our token encoder. We pass the ELMO embeddings through a feed-forward neural network to produce a vector of mean and a vector of standard deviations for each dimensions. And then we get the Gaussian distribution for each dimensions respectively. So recall that we have the cartoon trade-off curve. Now we will show you an empirical one. The cartoon and the empirical curves are consistent. The orange line means that the specialized embeddings have 256 dimensions, and the blue line means that the specialized embeddings only have 5 dimensions. Notice that when we keep less information, the blue line have better parsing accuracy than the orange line. This is because once we compress enough, we can keep all the information with a less noisy 5-dimensional compression, and it's easier to optimize in practice for a fixed number of samples. So for the same level of mutual information, the 256 dimensions has to contain more noise, so sampling would be bad. Our specialization is contextual because we are compressing from ELMO layer 1. So we achieve a specialized representation that's both contextual and contains syntactic information. But what do linguists do? So linguists use part-of-speech tags. Post tags are the conventional syntactically compressed representation. And sometimes linguists can use finer-grained super tags, like CCG taggings, which are specifically supposed to guide parsing. So could we get these discrete tags automatically? Well, yes, we can, and let's extend our method to the discrete case. So we put the continuous on the right-hand side as a comparison. The deterministic counterpart for discrete case is a one-hot vector. Notice in this example that only verb fires, and the other dimensions are 0. Our IB method is stochastic in that we have a multinomial distribution for this token, whose probabilities sums up to 1. But actually, we don't know the correspondence between dimensions and part of speech tags, and we don't even know if there is a correspondence. So we will just call them by their indices. Like maybe dimension 3 and dimension 4 are different forms of nouns. So here, we are again using randomness to forget whether an object pronoun is plural or singular. Here is the discrete architecture. We use a very similar structure, a feed-forward nonlinear neural network to produce parameters for a softmax distribution. And finally, we pass through a softmax layer to generate the multinomial distribution. So now, let's zoom into the parser. We use a dependency parser that takes in a vector representation for each token. Note that there is a slight disparity. The output of our token encoder is a Gaussian distribution over specialized tagging or over specialized embedding vectors or a multinomial distribution over discrete tags. But the input of the parser isn't a distribution. It's a specific vector or tags. Our objective requires us to average parse log likelihood over the distribution, so we need to sample and average. Because we have a sampling step in the forward pass, we will have to consider how to estimate the stochastic gradient in the backward pass. Luckily, there are principled ways to do this. So for the continuous case, we use the reparametrization trick, and for the discrete case, we use the Gumbel softmax trick. So to minimize the IB objective directly, some terms are intractable, like P of parse given grain and P of grain. So we instead minimize a variational upper bound, which is what the previous slide actually estimated. For mathematical details about why those two terms are intractable and the detail about the upper bound, please refer to our paper. So do our specialized tags correlate with the traditional part of speech tags? Well, yes, they do, and here are some results. So first, let's look at some t-SNE plots. Each dot represents a word token and is colored by the gold part of speech tags. So when we keep all the information, we could see the clustering, but the boundary is not clearly separated. And when we have moderate compression with a good beta value, we have very clear clustering of part of speech tags. But when we have too much compression with a big beta value, everything will just mix together. So for the discrete case, we run deterministic annealing to get a hierarchical clustering result of the discrete taggings. We start from beta being very large and a happy Oscar, and we gradually anneal beta down. We keep more information, which use finer-grained taggings at Oscar's expense. So poor Oscar. The hierarchical clustering result successfully captures these big categories like adjectives, verb, nouns, etc. The cute part is that as we get more finer-grained, they also captured clusters like possessive pronouns, nominative cases, accusative cases, and anaphors. So our result agrees with the intuition that part of speech keeps information about parsing. Part of speech tags are contextual, and ours is contextual as well. However, the word type should also be a strong predictor of part of speech tags. So how do we specialize so that our specialized taggings mostly depends on the word type information? So a simple solution is to use Elmo layer 0 because it's based on a character level convnet, so Elmo 0 is not contextual. Specializing is to extract from existing embeddings, so it's also non-contextual. We propose a soft version, making the specialized taggings depend mostly on its word types. So we add the conditional mutual information term. To minimize this term is to say that as we introduce the context of each word, our specialized taggings do not contain much extra information than if we only look at the word type. So we compare to 3 baselines in terms of parsing accuracy for the continuous case. PCA in green is task agnostic, and it doesn't really help the blue baseline of ELMO. MLP is in yellow is like our method. It helps ELMO, but it keeps the same amount of information for every token, whereas our method in red keeps Oscar happy. So our method outperforms the 3 baselines. Now this graph only shows English, but we run experiments on 9 languages. Our method wins or statistically ties across all 9 languages. We have approximately 1-point improvement on labeled attachment score on average. And the gold part-of-speech tags are good for parsing. But the point of our method is to find the tag set that's most useful for parsing. And our result outperforms the part-of-speech baselines unsurprisingly. So now we thought you might have a question. Sure, thrashing works, but does it work as well as fine-tuning? And we ran an extra set of experiments just yesterday, so on English, poor us. It turns out that we actually did a little better than fine-tuning. The difference isn't statistically significant. But a caveat is that we didn't do an extensive hyperparameter search. We swapped only one fine-tuning hyperparameter, namely the weight decay, just as our thrashing method swapped only the beta parameters. Now, well, that's how most people fine-tune in practice as well. So we know that if you burn a lot more periods, maybe fine-tuning will win. But if you want something cheaper and effective, thrashing is both cheaper and more effective than basic fine-tuning. And thank you so much.
Okay. Any question?
Okay, thank you for your presentation. And I saw you take ELMO as for example, but if people want to use other kind of language models like XNet and BERT, what are the requirements that they need to consider? And I see that you are trying to use the different layers from the ELMO. So if people are wanting to use other language models, what kind of layers they should consider, or what kind of characteristics they should consider to use this? Thank you.
So this method is very generalizable. You can just, well, we're using ELMO just as an example. You can just easily use BERT, basically by swapping the input from ELMO to BERT. And then in this case, for detailed analysis, we use different layers of ELMO, but we could also just easily extend our framework to use all ELMO by concatenating the 3 layers together, or just simply swapping. We have more details in our paper about using different layers of ELMO as well.
Okay. So thanks our speaker again.